Welcome to Abby's instructional video on how to do math.
For part A, I chose question 2, which is consider the curve y equals x cubed minus x squared minus x plus 3. For question I, we'll be finding the stationary points and determining their nature. We've written up the equation up the top there. We'll start by deriving, just by timesing the indices and minusing one off. We'll double derive as well, just so we can make sure we are ready for the next part of the question. We are now going to make the first derivative equal to 0 to find our stationary points. We do that and then we factorize. It doesn't really matter how you factorize, your way, whatever way works easiest. I just use the cross method because I find that the easiest for me. Again, this is just to find our x values. So once we factorize, we'll be able to find the x values, and those will be our x values for the stationary points. As you can see, x equals 1 and negative 1 1/3. So after this, we'll be subbing it in to our original formula just to find our y values. For the next part, we're just subbing 1 into the equation, so it's 1 minus 1 minus 1 plus 3. That one's quite simple, so I haven't written that one down, but the next one I have. We go y equals negative 1/3 to the power of 3, and so on and so forth, and we should pop that into your calculator and you'll be able to find the answer for that one. As you can see, it comes to 3 with 5 over 27. Once we have our stationary points, we're going to test if they're minimum or maximum now. To do that, we are going to sub the x values into our double derivative and test if they are larger than 0 or smaller than 0. As you can see, I'm subbing in 1 now. This one is quite a simple equation. It just comes out to be 4, which is greater than 0, which actually means it's a minimum point and it's a concave up. For the next one, we'll be testing. We end up getting a negative 4 answer, which is less than 0 and will be a maximum point. That's all for this question, as that's all it's asking. For question II, it's given that the point P lies on the curve. Prove there is a point of inflection at P. It gives you point P, but I'd like to check to make sure it's actually a possibility for a point of inflection. To do that, I make the double derivative equal to 0. And then I solve for x. Making sure that's equal to the actual x value they give you, then I'm going to sub that into the original equation just to find the other one, which you get the 70 over 27. Now this is a possible point of inflection, but we're now going to test to make sure it is actually a point of inflection. To do this, we're going to test our concavity. So to do this, we're also going to use the double derivative and sub in points either side of the x value to find the concavity on either side. So I'm using 1 and 0 as a easy to use. So the first one comes to 4, which is greater than 0, so it's a minimum point, which also means it's concave up. For the second one, I'm using 0, which means it's going to be equal to negative 2, which is less than 0, which means this one's a maximum point and concave down. This means that the concavity changes either side of the point, which means it's actually a point of inflection. For question II, we're going to sketch the curve, labeling the stationary points, point of inflection and y-intercept. I've already gone ahead and wrote our stationary points and point of inflection up. So we're going to start by finding the y-intercept. To do this, we're going to make all the x's 0 in our original equation. Therefore, our y-intercept is 3. Now that we have all our points, we're going to pop them on the number plane that I've drawn up with our x and y axes. I've started with the y-intercept, and I've also started with the stationary points. Just doing all the dots is essential first, just so I get a rough layout. We know the first stationary point is a minimum, therefore it's concave up, which is the 1, 2 value, and then the other one is concave down. Now all we have to do is connect the dots and label the points. For part B, I chose question 1. A rainwater tank is to be designed in the shape of a cylinder with radius r meters and height h meters. The volume of the tank is to be 10 cubic meters. Let A be the surface area of the tank, including its top and base, in square meters. In part I, it's given that A equals 2 pi r squared plus 2 pi r h. Show that A equals 2 pi r squared plus 20 over r, when A is the surface area of the tanks. So pi r squared comes from the surface area of the circles, and it's just times by 2 for the top and bottom. The pi r h comes from the circumference times the height. It's given in the question that volume is 10 meters cubed. The formula for volume is actually pi r squared h. This is the area of the circle times the height. From then on, we will relate the volume together. So pi r squared h equals 10. We're going to get h out the front so we can get rid of h in the original formula. So h now equals 10 over pi r squared, and we're going to sub this into A, the one that we are given. So A will now equal 2 pi r squared plus 2 pi r in brackets 10 over pi r squared. Now we're just going to simplify this down. I started off by timesing 2 pi r by 10 over pi r squared, which just ends up being 2 pi r times 10 all over pi r squared, which simples down to 20. You can cancel some of the pi's and the r's, and you end up with 2 pi r squared plus 20 over r. This is also equal to the equation that we are trying to prove. In question II, we are to show that A has a minimum value and to find the value of r for which the minimum occurs. So for this, we're going to use the equation that we've just proven in the last question, and then we're going to derive this one. So that will equal 4 pi r minus 20 over r squared. This one comes from the 20 r minus 1, just moving up the r to the top, and then I derived from there and put it back underneath. So we're also going to be doing our double derivative, just like in the very first question that I did. So it'll just be 4 pi plus 40 over r cubed. This time, to do this, I did the same process as last time, just negative 20 times negative 2 this time, which equals a positive 40 with an r negative cubed. And I just pop the r cubed back underneath to make it not negative. Now, just like in any maximum or minimum question, we're going to make the first derivative equal to 0. This one's quite a little bit of a tricky one. I'm going to times out the r squared onto both sides, so that it equals 4 pi r cubed minus 20 equals 0. Then I'm going to move the 20 over to the other side, making it a positive 20, and dividing 4 pi onto that. I can actually cancel out and simplify that one to 5 over pi, and then you can cube root to the other side to get rid of the cubic. Then we're going to sub that value into our double derivative to test if it's a minimum value. We actually get lucky in this one, as we already have a value for r cubed from our last equation. It gets rid of the cubed root and we end up with only 5 over pi. And you can simplify this by putting the pi up the top with the 40, so it ends up with 40 pi over 5, which you can cancel down to 8 pi. So we end up with 4 pi plus 8 pi, which equals to 12 pi, which is greater than 0, which means this is a minimum point, which is exactly what we're looking for. Now, to find the r value, we're just going to sub the cube root of 5 over pi into a to find the y value. So this equals 2 pi in brackets cube root of 5 over pi all squared plus 220 over cube root of 5 over pi. We end up with an answer of approximately 25.7. Therefore, our final minimum value is at cube root of 5 over pi and 25.7. That's the end of this video, and I hope you learned some maths.